The art of algorithm analysis, mastering efficiency in code design in the ever-evolving world of software development. Understanding how algorithms perform under different conditions is not just beneficial, it's essential. This guide delves deep into the principles that govern algorithm efficiency, helping you navigate through complex computational problems with precision. Whether you're optimizing existing systems or designing new ones from scratch, mastering algorithm analysis can significantly enhance your problem-solving toolkit. It equips developers with critical insight into resource utilization and scalability challenges they may encounter along their journey. Understanding the foundations of algorithm analysis. Algorithm analysis begins by examining what an algorithm actually does when executed. At its core, every algorithm processes input data according to predefined instructions to produce output results within specified constraints. This foundational knowledge sets the stage for evaluating performance metrics such as time complexity and space requirements. By focusing on these aspects early on, programmers gain clarity about potential bottlenecks before implementation even starts. An effective approach involves considering both best-case scenarios where everything aligns perfectly and worst-case situations that could arise due to poor input distributions. These extremes help define upper bounds for expected behavior across various applications domains. Beyond theoretical discussions, practical implementations often reveal hidden inefficiencies not apparent during initial design phases. Therefore, continuous evaluation remains crucial throughout the entire lifecycle of any given project involving substantial computation workloads. Evaluating time complexity through Big O notation to accurately measure how efficiently an algorithm operates over varying dataset sizes, developers rely heavily on Big O notation, a standard method used universally among professionals worldwide. Big O expresses growth rates relative to input size rather than absolute runtime measurements which vary based upon hardware capabilities and other external factors beyond our control. For instance, while sorting 10 elements might take negligible time regardless of methodology chosen, scaling up dramatically impacts execution speed depending largely upon selected techniques employed during processing stages. Commonly encountered complexities include constant time operations denoted by $O(1), linear relationships represented via $O(n), quadratic expressions found frequently in nested loops, $O(n²), logarithmic behaviors seen especially in divide-and-conquer strategies, $log n, and exponential patterns typically associated with recursive backtracking solutions, $2 to the power of n, $1 operations whose duration remains unchanged irrespective of input scale. Ideal scenario for optimal efficiency, log n efficient handling of growing datasets through having mechanisms common in binary search implementations, n linear progression indicating direct proportionality between input volume and required processing efforts, n log and slightly less efficient but still viable solution path observed commonly in quicksort variants, n superscript 2 quadratic increase suggesting need for optimization, particularly noticeable when dealing with large arrays. Recognizing these classifications allows engineers to make informed decisions regarding trade-offs between simplicity versus performance improvements achievable through alternative approaches tailored specifically towards particular application needs. Space complexity considerations beyond just memory usage. While many focus primarily on temporal efficiency gains offered by improved methodologies, neglecting spatial implications can lead to disastrous consequences affecting overall system stability and responsiveness negatively. Space complexity refers precisely to amount memory consumed during operation lifecycle, including temporary storage allocations made transiently yet cumulatively contributing toward total footprint maintained concurrently active tasks. Certain algorithms require auxiliary structures, increasing overhead substantially compared to others utilizing only minimal additional resources, maintaining lean profiles advantageous, particularly mobile environments constrained physical limitations. It's vital, therefore, always balance between computational power demands against available hardware capacities, ensuring neither side gets disproportionately prioritized, potentially causing cascading failures elsewhere unanticipated initially. measuring actual performance versus theoretical predictions despite rigorous mathematical modeling providing invaluable guidance. General trends likely outcomes faced real-world deployments occasionally diverge expectations rooted purely analytical frameworks alone. Factors influencing discrepancies range from cache locality effects inherent modern architectures favoring contiguous accesses improving retrieval speeds, unexpectedly benefiting seemingly suboptimal choices, theoretically inferior alternatives. Hardware-specific optimizations play significant role determining actual throughput experienced end users despite identical asymptotic guarantees promised abstract-level descriptions. Thus combining empirical testing alongside formal analysis yields most robust conclusions capable adapting evolving technological landscapes continuously reshaping underlying infrastructure supporting day-to-day activities seamlessly unnoticed background. Case studies illustrating practical implications of different complexities consider classic example comparing bubble sort implementing straightforward pairwise comparisons versus merge sort leveraging divide strategy recursively splitting halves. Merging sorted components thereafter. Bubble sort exhibits $O(n superscript 2) behavior making unsuitable extensive collections whereas merge sort achieves $O(n)log n offering far superior scalability suitable managing vast amounts records effortlessly without perceptible delays. Differentiating clear advantages provided advanced methods becomes evident analyzing concrete implementations demonstrating tangible differences impacting user experience considerably. Such case studies reinforce importance selecting appropriate tools matching task requirements avoiding pitfalls arising premature optimization attempting force-fit inappropriate constructs onto mismatched problems resulting unnecessary complications. Later stages maintenance cycle. Trends in modern algorithm optimization techniques. Recent advancements computing technologies introduce novel paradigms redefining conventional wisdom surrounding traditional approaches previously considered optimal standards industry benchmarks. Parallelism now central theme enabling simultaneous execution independent segments reducing wall clock times significantly even modest multi-core processors readily accessible nowadays commonplace devices. Machine learning integration facilitates adaptive algorithms dynamically adjusting parameters runtime-based historical patterns identifying emerging tendencies proactively mitigating future risks preemptively rather reacting after damage inflicted already occurred. These innovations underscore necessity staying abreast rapidly changing field embracing flexible mindsets open experimentation exploring unconventional avenues pushing boundaries established norms continually strive excellence wherever applicable possible. Best practices for effective algorithmic thinking developing strong analytical skills requires cultivating mindset-focused problem decomposition isolating individual functionalities simplifying intricate puzzles manageable pieces. Amenable thorough examination each component independently. Practice regularly solving diverse types questions ranging simple exercises requiring minimal steps progressively challenging scenarios demanding deeper conceptual understandings multiple layers abstraction necessary tackle effectively. Engaging actively online communities participating contests competitions exposes practitioners wide array. Perspectives solutions foster collaborative spirit enhancing collective intelligence pool shared experiences accelerating personal growth trajectories substantially faster rates than isolated study efforts alone. Documenting thought process meticulously aids refinement reviewing past attempts uncovering blind spots overlooked first pass encouraging iterative improvement cycles leading breakthroughs eventually refining raw ideas polished final products ready deployment. Conclusion mastery algorithm analysis empowers developers create resilient scalable systems adept handling varied workloads gracefully regardless environmental fluctuations unpredictable nature digital landscape. By integrating theoretical foundations practical experiments remain vigilant current developments ensure continued relevance professional practice adapt swiftly emerge technologies shaping tomorrow's computing ecosystems today.